So thank you very much for the introduction. As I said, my name is Maslanka, and I'm going to be presenting today on watching the world burn, satellite insights into global wildfire activity. I'm going to there's going to be a lot of different bits, lots of different images and various different satellite observations, but I would like to start with this one here of a wildfire that's happening over, or that happened over in Siberia, in Russia, I believe it was in 2021. And it's actually showing the same fire, but just showing it from different viewpoints. So you have one image on the left, which is the true red, green, blue image. So that would be how we would see, how if we were up in space looking down onto the Earth, how we would see the fire. But then having a look, the one on the right is actually having a look and doing using some different infrared wavelengths and changing the way the colors are working, and that's actually allowing us to see through the smoke and actually looking at the burnt area and the fire underneath it. So it's a really nice insight into actually looking at a fire, but looking at it the same way, but in different perspectives. So a little bit about myself. So as was mentioned, my name is Dr. Will Maslanka. I'm a remote sensing scientist. I got my master's in meteorology and a year at Oklahoma at the Universities of Reading and Oklahoma University in the US. I got my PhD in looking at microwave remote sensing of snow, both at the University of Reading in conjunction with the Finnish Meteorological Institute. I've worked as a postdoc researcher looking at radar remote sensing of soil moisture for natural flood management with the University of Reading before moving to my current position, which is looking at high latitude wildfire observations and greenhouse gas emission estimations using Earth observation techniques at King's College London. So a little bit of an outline of this talk. I'm going to start off with a little bit of an introduction to wildfires. What do I mean by wildfire? Why do we care about wildfires? That sort of thing. I'm going to give an overview of the remote sensing of wildfires. So actually, how do we go about doing that? What is the little bit of physics behind that? What's the tools that we use? What do our images look like? That sort of thing. I'm then going to move into how global wildfire patterns change, and that's both through changes in anthropogenic sources and from natural sources. And then I'm going to cover a little bit about wildfire emissions of greenhouse gases, and I'm going to talk about a little bit about my research in trying to estimate them using polar orbiting satellites. So there's a range of disciplines that's going to be kind of touched upon during this talk. There's a bit of geography and physics, chemistry, a bit of meteorology, and a very, very small bit of statistics, but it is Friday afternoon, so I'm going to try and keep that to as much of a minimum as possible. So I'm going to start off with, what do I mean by wildfire when I say, or talking about wildfires? And it's kind of difficult to come and pinpoint exactly like a definition, but I really like this one from the UN in one of their more recent supports about looking into wildfires, that a wildfire is an unusual or extraordinary free-burning vegetation fire that poses significant risk to social, economic, and environmental values. It can be started maliciously, accidentally, or through natural means. And I quite like this as a kind of catch-all definition, because not all environmental fires are bad. Because when we have the image of the wildfires, like we've got the picture here, you imagine that this is kind of like, this is going to be terrible devastation, and there's going to be a massive loss of ecosystems and things like that. And while that is true for our large wildfires, fire is an important land management tool, and it's got important cultural, economic, and ecological ties. So when I say that it's not all fire is kind of bad, it's a naturally occurring phenomena. Burning of older trees allows the canopy to open up for saplings and for new growth underneath. So it's a way of clearing out some of the older vegetation to allow the new to grow. And in fact, there are some types of vegetation, such as the lodgepole pine in North America, that's evolved to actually produce cones that only open and release the seed once they've been exposed to high temperatures. So they need fires in order for the forest to grow. So it's important to have a look and to know that it's not all fire is as such bad. But when I'm talking specifically in this talk about wildfire, I'm talking about the unusual or the extraordinary large fires that we kind of see. So moving on from what do I mean to what does it need? This is a fire behavior triangle. It's kind of a nice simplistic diagram to kind of show the different elements that is needed to explain the behavior of a wildfire. It's very similar to the fire triangle that you kind of go about when you do fire safety courses, when you talk about the fire needs oxygen, heat, and fuel. It's just slightly different things that are needed because of the scale of the fire. So all wildfires, to start off with, they need an ignition source. As we said in the definition, that can be accidental, natural, or malicious. So natural sources would be a lightning strike onto dry grass or to dry vegetation could cause a wildfire. Accidental could be a landscape fire, or it could be a farm management practice that's got out of hand, or something like a campfire that's then been left unattended, that has then caught the canopy. And then when I say malicious, I'm talking about there can be aspects of arson, where people set fires on purpose in order to cause massive amounts of damage. The wildfire itself is its behavior is dictated by elements of topography. So kind of like what sort of the shape of the land, what type of hill is it on, if the fire is moving uphill, downhill, those sorts of things, because that will dictate the strength and the speed of the growth. It's also impacted by weather and by fuel, because weather would be something like depending if you've had a drought, so you've had a long hot period of time, not a lot of rainfall and precipitation. It means then that you've got conditions that are more indicative of wildfires and more indicative of wildfire growth. And likewise with fuel, if you're going to have a lot of vegetation and a lot of dry vegetation, then that is more indicative of growth. Whereas if you have vegetation that has got a lot of moisture in it and a lot of moisture on it, it is less likely to grow as a fire. And these three kind of main points kind of impact each other. So the topography can impact the weather and can impact the types of fuels, the type of vegetation or the biomass that's being grown and is burning. And the fuel and the weather themselves kind of impact each other as well. So it's a real difficult and complex to try and pinpoint exactly which bits of what kind of impact the fire, but all three of those kind of points impact the fire themselves. So this is kind of like what a fire is and how it works, but why do we care about where the wildfires are? So as we were saying before, there's a real societal, economic, and environmental risk that comes in with wildfires. On the societal risk, if you have fires that are close to urban areas, there is the risk of massive loss of life and destruction of homes, and can be quite catastrophic. The news articles or the news headlines on the right was just a quick scrape just off of BBC News of fires that happened over the end of last year and the beginning into this year, and talking about the risk of fire that's happening. So kind of the societal risk is usually the really big news articles that kind of happen, is when it shows that it's actually, we care because there's a real risk to people and to livelihoods, and to homes. But also on the other front of that is you've got a degradation of air quality, because the fires will emit a large amount of smoke, and that then people will breathe in the smoke, and that causes globally hundreds of thousands of early deaths every year, especially in some areas in like Southeast Asia and sorts of places like that. It's important in societal risk for fire management, because firefighters, especially in the likes of Canada and the US, for their large landscape fires, as well as places like Greece last year and in Australia, they need to know where the fires are so that they know where they can go and help put the fires out, evacuate people, that sort of thing. If you have wildfires that happen near areas of industry, you've got economic risk, because you'll have destruction of industry, supply lines, transport routes, those sorts of things, as well as potential, there's risk of damaging agricultural goods, things like trees, tree stock, and farmland and agricultural land will be a real issue, and is a real risk to their economics and their economic benefits. And then you've got the environmental risk, which is kind of where I come into wildfires, is that there's a real risk of loss of habitats and vegetation, but also you have the mass emission of particulate matter, so things like soot and greenhouse gases, into the atmosphere and onto the surface. And that's particularly where I come in. That's where I come in to try and assess the amount of the emissions from wildfires and how they're impacting the atmosphere. So as I kind of previously mentioned with the firefighters, in order for us to be able to assess the location of the risk, we need to know where the fires are. And we need to know that on a kind of a local scale, the regional scale, but also globally. And the only real way to do this at the scales that we need is via remote sensing from space and via satellite observations. So that we're able to get accurate and timely observations over large areas, that we're able to kind of see exactly where fire and where the smoke is going. So here we've got an image taken from one of the polar orbiting satellites of fires that was happening, I believe it's in Ontario, in June of last summer, so June 2023. And this is looking at the fires that were happening there at the beginning of June, but the smoke then that was being blown from Canada down into kind of the New York area, and then was having a lot of problems, causing a lot of problems in the New York region, and looking at especially with JFK Airport. So it's kind of showing that we need the satellite observations because, especially with smoke, it's not a country-specific problem. Smoke will go wherever the wind takes it. So we need to be able to have a look and see from the big atmospheric patterns to know exactly where the smoke is going. So that's a bit of a whistle-stop tour as to why we want to know about wildfires. This is now kind of going to start to talk about a bit of an overview of exactly how we go about that. So this is going to be the basics, and it's going to be the very, very little bit of physics that's going to be touched upon here, is that the way in which that we do the remote sensing of wildfires is we look at the observation of energy that's been released by the wildfire. So in this sense, when I say that the energy of the total energy that's released, about 10 to 20% of that is released in the electromagnetic spectrum. And of that, most of that's in the infrared band. So what we're able to do is that we can have a look at the energy that's released in that infrared band for fire areas, and we can actually distinguish that between areas and surfaces that aren't burning. So I've got an example of this. So we've got the plot here on the right. And what this is showing the spectral radiance across kind of that infrared band, but for 3 different surfaces at 3 different temperatures. We've got one at 300 Kelvin, which is the black line, and that's simulating our normal conditions. That's our ambient temperature of a surface that isn't on fire. You've then got the red line, which is at 600 Kelvin, which is showing a smoldering fire. So it's the temperature of a typical smoldering fire. And then you've got 1000 Kelvin, which is the kind of orangey yellow line. And that's our flaming combustion line. That's kind of when you have a look at the image that I was showing of the fire previously, that sort of flame. And what you can actually see is that the energy that's released, the spectral radiance of the different surfaces, is very different for the flaming surfaces and the smoldering surface than it is for the non-smoldering surface. And it's actually orders of magnitude different. So what we're able to do is then use that interaction and use those orders of magnitudes of difference to detect of areas that is on fire compared to areas that aren't on fire, and then figure out how much power the fire is producing, so we can then have an estimation of kind of the strength of the fire. And that's the work that I do. So that's under active fire observation, and that's where we detect pixels in the satellite that's burning at the time of an overpass. It says they're under relatively cloudy-free conditions because the clouds are able to block our views from the satellite, but I'm not going to go into too much detail at the moment. And the main kind of data that we get out of that is what's known as fire radiative power, and that's the amount of energy that the power that the fire produces over a certain area. We're able to have an idea of how much energy it's released by getting a fire radiative energy, or FRE, and that's where we just take the fire radiative power and we multiply that through time, through all multiple observations. The other main part of remote sensing of wildfires is looking at burnt area. So that's a bit of science that I don't do, but I know a fair bit about it. And that looks at mapping spatial extent of fire and vegetation loss. And that can use a little bit of active fire detection just to validate where the fires are, but it also uses multispectral data so that we can have an extent and have a look at burn scars to see how much of an area has burnt. So that's where we get data from spatial extent. And we also are able to have a look at dates of areas that are in remote places and see when they burnt, by having a look at the satellite times and knowing when they passed and when it was burning and when it wasn't burning. So that's pretty much the basics. The tools in which we use that and do that with is with, as I say, with satellites, with both polar and geostationary satellites, because space-based remote sensing is the best way to get global coverage. So I use mainly polar orbiting satellites. So those are the ones that you can see that are whizzing around at the moment. They orbit kind of north to south, south to north, and they take swath observations. So they're basically having a look at a certain point in time, and then just having a look at the data that is underneath the Earth as it is orbiting. These have really high spatial resolution, so we're able to get pixels that are less than a kilometer in size, so we can get some really good observations of fire and of smoke using them. But they have poor temporal resolution for a given point in time, because we have to wait for the orbit to actually align with with the point we're looking at the ground. So we may get 2 or 3 different points of an observation with any given satellite. There are 3 main instruments that are used on 7 satellites for active fire observations. We've got the MODIS instrument that's on the Aqua and Terra satellite that's run by NASA. We've got the VERS instrument that's on SALMI, MPP, and the Joint Polar Satellite System that's run by a mix between NASA and NOAA. And then we've got the SLSTR instrument that's on Sentinel-3A and 3B that's run by ESA. If we're wanting to look into burn area and extent, then we need to have a bit more of multispectral observations. So we're able to use other instruments like Sentinel-2 that's run by ESA, and Landsat that's done, I think it's done by NASA. So we're able to use those to have a look at burn extent. We've also got geostationary. So unlike polar orbiters that orbit north to south, these effectively orbit east to west, but they no, west to east, I think it is, but they're able to go and have the same orbital period of that of the Earth rotation. So what that means is that it's able to get a full disk observation all the time, and it's looking at the same points on the Earth. So that means then we're actually able to get really a high temporal resolution. So we get observations every 10 or 15 minutes of the full disk. Because it doesn't really move in latitude outside of orbital corrections or outside of calibration movements. But the issue we have with those is that they have poor spatial resolution at the edges of the disk because of the way the view geometry works. We have smaller pixels in the center of the disk, but they get larger the further away from the center you get. So while it's really good for looking at fires, say, over Africa, they're not very good at looking at fires over the Arctic. So there are 5 geostationary satellites that we use for fire observation. We've got GOES 18 and 16 over the east and west coasts of the US and South America. We've got MSG2 and MSG3, so that's Meteosat second generation satellites run by ESA over kind of east and west Africa that allows us to catch all of Africa and Europe. And then we've got Himawari 8 that's run by the Japanese Meteorological Agency that is then placed over kind of the Southeast Asia region, and we're able to get bits of Japan and parts of China and parts of Australia as well. So those are the satellites that we use, but we now kind of go into what kind of data do we collect. And this is an example of our low Earth orbit data that we get from, this is specifically with VERS using SMPP, over some fires over the Southeast Australia in the end of 2019. We've got the true color image on the right. So you can see there the red soil, you've got the blue of the ocean. I've got the outline of Australia highlighted there in cyan, just so that we're able to kind of really see exactly where it is. You can also make out clouds, and then you can begin to make out the smoke and some of the haze that's there. On the left, we've got our actual active fire product. So here we've got gone through our algorithms, and it's able to calculate where is non-burning vegetation or non-burning land in the green, indicate where there's water in the blue, where there's cloud and smoke in the white, and then where there's red, there's fire pixels. And that's where we're actually indicating in the satellite where there's fires. We're able to get the information from the FRP, so the power out of that, and we can really pinpoint geographically where they are, so that when we transpose them across onto our RGB image, it gives us a lot more context as to what is smoke, what is cloud, and it allows us to build a bit more of a bigger picture. It doesn't just work in, say, in Australia. We've got an example here from the fires that are happening in Greece in the summer of last year. So we've got, here you can see on the right, you've got smoke that is going over the North Aegean Sea. In our product on the left is actually being flagged as cloud, because it's quite difficult to pick out what counts as cloud and what counts as smoke, because they're in the eyes of the satellite, they can be quite similar. But when you move across the fire data and move that onto the RGB data, you can really pinpoint exactly what's cloud and what's smoke. So it's really good in that instance. Likewise, works well in remote areas. So this is an example of an observation that was happening over northwest Canada. I think this is in the Yellowknife area over the summer of 2023. And you can see there we've got lots of cloud, a lot of cloud, a lot of smoke, a lot of haze. And it's quite, in the left, you can see it's actually having difficulty picking out what's land and what's water between the blue and the green. However, when you move across the fire data, you can actually really pinpoint and see exactly where they are. And it still does a really good job of picking out the fires because of that difference in spectral radiance that we talked about a little bit earlier. So that's kind of like a nice broad brush thing of talking about wildfires, how we go about it, why do we care, and how do we do it. I'm going to kind of move on a little bit now into how we're seeing wildfires change. So this is also going to be a bit of a broad brush explanation, because going into the specifics gets quite difficult and quite complex. And it's a bit easier just to talk about it in kind of hand-waving motions rather than exactly which areas are likely to see more fires because of this single point of this single source. I've put the fire behavior triangle back up onto the slide just so that you can exactly see what I'm talking about and which impacts and how it's being impacted. So we can see that actually, global wildfire activity is impacted primarily through changes in fuel and in weather, but also there's a little bit of changes from ignition source. And these changes come from both anthropogenic and from natural sources. So first off with anthropogenic, when I'm talking about the anthropogenic, I'm talking about human-induced changes. So first off, we've got human-induced changes of the landscape, so actually of the land and the stuff that is burning. So we've got changes in ignition sources bit from human influence, because of the way that we use fire. We would use fire to burn, it has been known to be used fire to burn off forested areas and to manage agricultural areas through like slash and burn techniques in the Amazon, things like that. That sees a net increase in ignition sources compared to the natural variability, just because that we're putting more fire onto the ground. So there's more ignition sources, there are more fires happening. We see influences the changes in fuel, because if we've got, say, the likes of logging or cattle grazing and slash and burn, we're reducing the amount of available fuel that's there because we're removing biomass, we're removing vegetation and allowing other stuff to be there. So we're reducing the amount of stuff that is there to burn. But on the other side of that coin, through abandonment or reforestation, we're actually increasing the amount of vegetation that's there. And that means then that we're increasing the amount of fuel that's there. So we as humans are increasing the amount of stuff that's available to burn. You also have something that's called land fragmentation, and this is where it doesn't kind of abandonment and logging and cattle grazing happens at different times in different places. And this can have a different impact depending on the type of biomes, depending on if you're in a rainforest or forested area compared to in like the savannah. So it's a bit difficult to piece that apart, but it can be a real issue, and it can be have different impacts and different changes. We also see human influence change on the weather with respect to landscapes. So an example of this is if you were to have a large area that gets deforested, where you have a larger area of logging that gets cut down, you would see that would be impacting regional evapotranspiration, because there is a reduction in the amount of transpiration from vegetation of moisture from the ground into the atmosphere. That would result in a lack of cloud cover, because there is now less moisture in the air. So there would then be less clouds to form, which means there would be less precipitation. So that would provide potentially a regional local drought. If we're having a local drought, that means then that our fuel is going to be drier, and it also means that the weather is providing us the conditions that it means that we're going to be more likely to see wildfires. So you can begin to see how they all start to can be quite busy, and it can be quite difficult to piece exactly where things are going and what changes because of what condition. It wouldn't be a thing talking about anthropogenic changes if we didn't mention climate change. So human-induced climate change does influence the weather. We're seeing a increase in global temperatures or global average temperatures going up, especially compared to pre-industrial era times. And what that basically means is that through higher temperatures and through changes in rainfall patterns and rainfall anomalies and changes in the wind patterns, wind strength, and the seasonality of that, we have been altering the wildfire season, which means that we're actually increasing the conditions for wildfires to happen earlier and to happen later. So wildfire seasons are longer. In addition to the climate change influencing the weather, it influences the available fuel, because an example of this would be thawing permafrost that's happening in the Arctic, where it would originally have been frozen, so it would be unable to burn. Because it's now warmer and it's now melted, it means that actually we've got permafrost areas and peatlands that were frozen that now can burn. So we've turned carbon sinks into carbon sources, and we've actually allowed more places. There's more places that are available to burn now. And also climate change. There's a discussion about how climate change can influence ignition sources. By having warmer temperatures, the air itself is actually able to hold more moisture in the air per given volume of air. Well, that means if there's more moisture in the air, there's the chance that means there's going to be more instability in the air, which would lead to more thunderstorms, and then could lead to more instances of dry lightning, which is then lightning that happens when there isn't rainfall, which means that there's more ignition sources happening. So we can see how it's already beginning to get a bit complex, and there's a lot of different things how they're impacted. It doesn't help with our anthropogenic climate change that it's actually what's known as a climate feedback loop. So we have climate change, which leads to more extreme weather. That more extreme weather leads to longer wildfire seasons and increased wildfire activity. Because we have more wildfire, we will have more carbon emissions, there'll be more thawing of the permafrost, and there'll be more biomass changes and biomass volumes, which then leads back into climate change, which starts the cycle again. And outside of this as impacting, say, wildfires, by having more carbon emissions and having, say, soot and black carbon, that would, especially in the Arctic, that can be emitted and then would fall onto snow and sea ice and land ice, which then changes the amount of radiation that area of land absorbs or reflects, which means that if you have snow that has black carbon on it, it is more likely to melt or melt quicker than if it was snow that didn't have carbon on it, which then changes sea level rises, levels and things like this. So it's a real, already it becomes just a spaghetti mess of different things and how they're all impacted. It's not just anthropogenic change, reasons that cause change. We have got natural sources of change. So an example of this is El Nino, or to give it its full kind of proper name, the El Nino Southern Oscillation, or ENSO. And this is an oscillation of sea surface temperatures in the Pacific that alters how heat is transferred across from the oceans to the atmosphere in a given year or a given time period. What that does is that will then, because of where the change in heat is, how the heat is being distributed, that will influence global circulation patterns. So where big storms are, where big high pressure systems are, where rainfall patterns go, which means that's beginning to impact regional temperatures and rainfall patterns, and it's changing the behavior of the wildfire. This is why the triangles come back up. So it's really it's difficult to piece apart what is a natural reason or what is an anthropogenic reason for why wildfires could be getting bigger or could be impacting in more places. But an example for ENSO of how ENSO changes wildfires is that during El Nino, so during what is known as the warm phase of ENSO, the conditions in Australia and the Northwest Pacific, so the Alaska, Canada, British Columbia region, tends to have conditions that is more indicative of wildfires. So it's natural reason. It always El Nino and La Nina oscillations have always been happening, but it just shows how there's natural sources of change as well as our human-induced sources of change. So up to this point, I've kind of been talking mostly on fires and how fires are kind of where they're changing and how we observe them. But smoke is another big part of this, and it's another big part of why we care about smoke, why we care about the wildfires. And fires contribute to the net buildup of atmospheric CO2 due to either combustion, due to deforestation after transferring kind of the carbon from the vegetation up into the atmosphere, and from peatland burning. So they emit a whole sort of things, from black carbon, different particulate matters. We've got trace gases and greenhouse gases like carbon monoxide, carbon dioxide, and methane. And to kind of give an idea of the extent of scale of how much is released, about 25 to 35% of the total CO2 emission into the atmosphere comes from wildfires. And that's on an annual basis. And it's so much so that that's why the World Meteorological Organization, the WMO, actually treats fire as an essential climate variable, as something that we need as scientists and as environmental monitoring community, that it's something that is very important that we observe and we have an account for. And just to kind of give a context, because like 20 to 35% is quite a large number for a single source, but it's kind of a relative number to give an absolute value. In 2023, 2.2 billion tons of CO2 was emitted into the atmosphere, and that's an estimation from the Copernicus Atmospheric Monitoring Service, or CAMS. And they do global observations and global estimations of where CO2 is and carbon is being emitted. And of that 2.2 billion tons last year, 22% of that came from the Canadian wildfires that happened over the summer. So it's a huge amount of CO2 that gets emitted naturally into the atmosphere. Going into that a little bit deeper and looking kind of a bit more into exactly what that looks like, we've got two different forms of observations. So on the left, we've got analysis of the daily mean organic matter aerosol optical depth, or AOD. And what that is a study of how much stuff is in the atmosphere when we're looking at things. So if it's particularly hazy, you're going to see the value is going to be increased. If it's very smoky, you're going to see values higher, or up to 1 or higher than 1. If you're having clear days, you're going to see values closer to 0. And what you can see here, as it's rolling through over the spring, summer, and autumn of 2023, you're going to see that kind of the fires that are happening over Canada and parts of the US, as well as fires that are happening in Siberia and up in the Arctic. And you'll be able to see exactly how the smoke is kind of transitioning and moving through the atmosphere. Especially when it comes through to June, you'll be able to see the fires that were happening kind of in eastern Canada that were impacting the US, but actually how they progress and move across over to Europe. So us here in the UK still being affected by smoke that's happening on the other side of the Atlantic. The plot on the right-hand side is showing the cumulative daily total wildfire carbon emissions for Canada. So this is basically looking at all of the carbon that's being emitted from wildfires for 2023 and for the 20 years previously. And it's showing that 2023 was an extraordinary year for Canadian wildfire emissions compared to the rest of the years. We can see that it's nearly 4 or 5 times the value of the 2003 to 2022 mean. And a lot of that is coming from these fires that are happening kind of frankly, across Canada. So it was a really, really big year for wildfire emissions in Canada. But how do we get those emission estimates? I was saying that we observe fires, but how do we get these observations? How do we get these estimates of how much stuff is being emitted into the atmosphere? And the emission estimates, kind of generally speaking, fall into two main categories, colloquially known as bottom up and top down. Bottom up techniques use information from burnt area and sometimes active fires, so that we're able to validate the burnt area from satellites to get an understanding of the amount of dry matter consumed, so the amount of stuff that burn. We get that from knowing exactly the burnt area. So the plot on the right, or the plot at the bottom, is showing burnt area regions for part of Central America. So the different colors dictate what time of the year it was burning, or what time, when it was burning, how long ago it was burning, that sort of thing. We also use information about pre-fire fuel load. So that's basically how much vegetation was there before the fire happened, as well as laboratory assumptions on combustion completeness, of an idea of how much of if we were to burn X amount, how much of that would actually burn, how much of that would turn into carbon, things like this. So knowing dry matter consumed, we can then get estimates of emissions for different types of compounds and things like that from using emission factors from specific biome types. So things like knowing the amount of how much CO2 would be released in the tropics compared to the temperate regions, or boreal or the Arctic regions compared to the agricultural or managed landscapes. And it's a really good, it's a popular technique. It works well, but there are some uncertainties that come in, especially around the pre-fire fuel load and the combustion completeness, because these assumptions, some of them are laboratory based, which means then that there's actually some empirical understanding behind that's gone on into that. And the assumptions that get used in that effectively end up with an error carried forward. They get put into the models and into the algorithms that do turn dry matter consumed into emission factors. And it means then that the uncertainty gets carried across. And they're actually the most significant source of uncertainty in this approach is in the understanding on the assumption of combustion completeness and pre-fire fuel load. The other technique, which is the way that I use, bypasses that the need for the laboratory assessment. We don't use we don't try to calculate the amount of dry matter consumed. We don't use pre-fire fuel load. We don't use combustion completeness. It directly relates the amount of energy that has been released from a fire to the amount of particulates, either from total particulate matter or from a specific emission, from a specific species, as they know. So we're able to have a look at this. We can see for a fire, we can have a look and we know exactly how much energy that fire released, and we can have a look in another satellite and see how much of an emission was produced. And we can do that hundreds and thousands of times, and we can then build up a inventory of different biome types around the world. So one such approach of this is the one that I use, which is known as the fire radiative energy emission, or the FREM approach. And this directly links observations of active fires to total particulate matter, or more recently to carbon monoxide. It's been shown to work really well over Africa and Southeast Asia using the geostationary satellites, because it's having those 10 to 15 minutes observation times. It's really good that we can have a really accurate observation of energy, and then we can have use that and link that to emission estimates. Doesn't work over the high latitudes, say for the Arctic, because of the pixel size. Because we're now at the edge of that disk, the pixel sizes get too big. So I've been looking at using polar orbiting satellites to replace geostationary satellites and seeing if that could see if that can work. And we're doing that by using some polar orbiting satellites and having a look and getting an inventory and a database of different fires over different biomes, so that we can group them to get our emission coefficients, as they know. So kind of going through a very nice and quick way of how FREM works is that I use two different satellites. So I use VERS, that's on the SAOMI MPP, one of the polar orbiters, and that gives me multispectral observations of the fire. So that allows me to indicate and identify exactly where the plume is and exactly where the fire is, and calculate how much energy that fire is producing. So the plot at the top left is our true RGB image. So much like the bigger images I was showing before, this is how we would see it if we were looking on the satellite. And you can see there that we've got smoke. This is a fire that's happening I believe this is happening in Canada. It's in the Yukon in July in 2019. And you can see that you've got a nice smoke plume that's happening there near some snowy mountains. To the bottom left, so directly below the RGB, is one of my false color images, where I've replaced the red wavelengths and replaced that with near infrared imagery. And what that does is that then really highlights exactly where there's vegetation compared to where there's non-vegetation, because it makes the vegetation a bright red and it leaves non-vegetated areas the original color. So it's really good at pinpointing exactly where there's lakes, where there's smoke and where there's mountains and snow, and then where exactly there's vegetation. To the right of the RGB image is the aerosol optical depth, as the AOD. So that's kind of the proxy that I use for exactly how much smoke there is and exactly where the smoke is. And you can see that where there's that bright yellow in the center of the image, that's where the smoke plume is. So it's really clear that you can see exactly where the smoke is compared to clear air that's either side of it. The issue with just using AOD is that it doesn't work really well if it gets near clouds, or in this case, near snow and mountains, because the way the algorithm uses different wavelengths and uses different colors. It highlights that anything that is white ends up having a high AOD. So it pinpoints clouds as having high AOD, as they should do, because there's a lot of water molecules in there. But here it's pinpointing that it's saying that the mountain and the snow has a clear AOD, where I know it doesn't, but that's just an artifact of the fact that there's snow. So in addition to that, I then use another false color image. So that's the one beneath it, it's the middle plot. That is then false color of shortwave infrared, near infrared, and red imagery. That then allows me to cut through the smoke and see exactly where there's burning. So you can see it makes the snow a kind of like bluey color, a blue cyan color, but it means that the smoke plume is then kind of almost see-through. And I can now see what's known as the burn scar, or the area that has been burning. And then you can see that there's orange splodges around that burn scar area. That's the parts that are actually on fire. That's the fire that you can see. So in addition to this, I use Sentinel-5P, and that is then doing my observations of carbon monoxide. So you can see here that where there's the yellow on the bottom right-hand plot, the yellow is showing there's a real spike in carbon monoxide in that point compared to like the bluey areas where there's low carbon monoxide. So the way that I use all of this data, and basically I draw a polygon around the plume. So I go through in a lot more detail than I'm showing here, of exactly where the extent of the plume and the extent of the fire. And then I can use that to build masks to extract carbon monoxide observations for the plume. So I know exactly what carbon monoxide has been emitted by the plume. And I can also use it to extract the fire radiative power to calculate radiative energy. I've done this for hundreds of plumes. I think I've got about 800 that's in my database at the moment across different types of biomes. So I'm able to go and show examples of how different amounts of energy for different fire plumes relate to different amounts of carbon monoxide. So this is for deciduous needle-leaf forests in the Arctic across Siberia. And I know that for any given, for an amount of energy that the fire emits, I have an estimation of how much carbon monoxide is being produced. So I know that for every megajoule of energy that is released, I know that about 150 grams of carbon monoxide is released. So it's a nice and quick and easy way of giving an estimation of carbon monoxide emissions given fire. So it is really good in this method is that because I don't need a lot of the preloaded information, I don't need a lot of the other satellite information, I just need fires. I just need the fire information and the carbon monoxide information to build this database, to build these graphs. I can then just use this graph for other deciduous needle-leaf forest fires in the Arctic, and I can do it in near real time. So it's really good as an estimation for almost live monitoring of carbon monoxide. So that's kind of the end of the talk. So kind of in summary, I've gone through kind of an introduction to wildfires. I talked about the fire behavior triangle, about how they need fuel and weather and how the topography will impact the fires. I've given a brief overview of the remote sensing of wildfires, about geostationary polar orbiting satellites, and they're really the only real way to get regional, national, and global observations. So kind of the image on the right here is a true color image taken from Sentinel-2, but the pixel sizes for these are 10 meters. So it gives us a really, really high resolution data and high resolution images of exactly where the smokes are, where the smoke is, and using different combinations of bands, we would have a really good idea of where the fire is. I've talked a little bit about how global wildfire patterns are changing. The take-home message there that is under a warming planet, we're likely to see more fires. But the sources of changes are both from natural and anthropogenic sources. And I've talked a little bit about wildfire emission from greenhouse gases, and specifically about the approach that I use, the FROM approach for high latitude fires. If you're interested in anything else in any of this talk, or want to learn more about kind of Earth observation and wildfire understanding, the 3 Twitter handles there. You've got my research group, so the KCL Wildfire Earth Observation. We've released information and images from our field campaigns and from our papers that produce in satellite images and things like that. We've got the wider KCL Geography Department Twitter, which is always interesting to understand and see what is happening on the whole geography front. And then we've also got the NCEO Science handle. So this is the National Centre for Earth Observation, and they fund an awful lot of Earth observation from within the UK, not just on wildfires, but on carbon cycles, on vegetation indices, on methane release. There's a whole sort of thing. So it's really interesting, the sort of stuff that's going from there. If you want to know a little bit more about the work that we do, or that I do, and the work that we do as our group, the QR code there takes you to a YouTube video. It's about 10 minutes long that's been set up by our research group, and that goes into a bit more into detail into the observations that we take. So both our satellite observations of Earth, of wildfires, but also of land surface temperature, and then also the field work that we do. So I do satellite-based work, but my colleagues work on airborne observations by flying, basically putting instruments onto a plane and flying the plane through smoke and through these smoke plumes, and attaching them onto UAVs and getting information from there. And a little bit about our lab-based work that we also do as well. So with that, thank you very much. I guess I'll open up for questions.